Hello everyone, and welcome to today's video lecture, which is going to be about the Eta Functional Equation. I know that many of you are interested in and probably have heard about the Zeta Functional Equation, and the Eta Functional Equation is very closely related to that. And this is an equation that was discovered by Leonard Euler and then forgotten about for I think about 100 years. And then when Bernard Riemann published his Zeta functional equation in his famous 1859 paper, people over time became interested in the historical antecedents of that, and they rediscovered Euler's work on this, which is what I'm going to present for you today. So our goal for today's video is to derive, following Leonard Euler, a functional equation for the eta function. We're going to see that Euler's derivation is really a conjecture, but a very brilliant and intuitive one at that. And then we're going to see how Euler's eta function would have led him directly to a derivation of the zeta function, but that wasn't actually discovered until 100 years later by Riemann in 1859. So first I'm going to ask you to recall something about the zeta function, which is that it's defined by the infinite series formula zeta of x equals 1 over 1 to the x plus 1 over 2 to the x plus 1 over 3 to the x plus 1 over 4 to the x plus 1 over 5 to the x plus dot dot dot. And the eta function is basically the cousin of the zeta function. It's very closely related. It's the alternating version of the zeta function. So eta of x equals 1 over 1 to the x minus 1 over 2 to the x plus 1 over 3 to the x minus 1 over 4 to the x plus 1 over 5 to the x minus dot 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 plus dot dot dot. And you can watch my previous video on the zeta function and eta function where we derived that the zeta function and eta function are related by this formula. Zeta of x times the quantity 1 minus 2 to the power of 1 minus x, close parenthesis, equals eta of x. And this equation allows us to relate the values of the zeta function to values of the eta function. For example, we know that zeta of 2 is defined to be 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus dot dot dot, and that equals pi squared over 6. You can see my previous video on the Basel problem for a proof of that. Therefore, we know that eta of 2, which is defined to be 1 over 1 squared minus 1 over 2 squared plus 1 over 3 squared minus 1 over 4 squared plus dot 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 minus dot dot dot, equals zeta of 2 times the quantity 1 minus 2 to the power of 1 minus 2, which equals pi squared over 6 times the quantity 1 minus 2 to the negative 1. Well, 2 to the negative 1 is just 1/2, so this is pi squared over 6 times 1 minus a half, or pi squared over 6 times 1/2, and therefore eta of 2 equals pi squared over 12. We know that zeta of 4 equals pi to the 4th over 90, and therefore plugging in 4 into our formula, we find that eta of 4 equals 7 times pi to the 4 over 720. We know that zeta of 6 equals pi to the 6th over 945. Therefore, plugging in 6 to our formula, we find that eta of 6 equals 31 times pi to the 6th over 32 times 945. So again, you can watch my video on the Basel problem to see how those values were first computed by Euler, and it's pretty amazing how he did it. But more amazing still is that Euler then discovered a general formula for the values of the zeta function on the positive even integers, and found that these values are very closely related to the Bernoulli numbers. And here's the formula Euler gave. Euler discovered that zeta of 2n, where 2n is a positive even integer, is equal to the formula negative 1 to the power of n minus 1 times b sub 2n times 2 to the 2n minus 1 times pi to the 2n all over the quantity 2n factorial. And here, again, n is a positive integer, and b sub 2n is an even subscripted Bernoulli number. And so just to list the first few Bernoulli numbers, which are relevant to our values for zeta of 2n, we have that b sub 2 equals 1/6, b sub 4 equals negative 1 over 30, and b sub 6 equals 1 over 42. And you can watch my previous videos in the series about the Bernoulli numbers to see where those specific numbers come from. More generally, because we have a formula for zeta of 2n in terms of the Bernoulli numbers, and we also have a formula that relates zeta of x to eta of x, we can combine these two facts together to derive an identity for eta of 2n in terms of the Bernoulli numbers. And that formula is eta of 2n, again where n is a positive even integer, equals -1 to the n minus 1 times b sub 2n times pi to the 2n times the quantity 2 to the 2n minus 1 minus 1 all over 2n factorial. Note, however, that while Euler was able to find a formula for eta of 2n and zeta of 2n, where 2n is an even integer, he wasn't able to find a formula for odd powers, so 1 over 1 cubed plus 1 over 2 cubed plus 1 over 3 cubed, and so on. And in fact, we still don't have such a formula even today. Fortunately, we're not going to need such a formula for what we're about to do, because in addition to studying the convergent series of the type 1 over 1 to the n minus 1 over 2 to the n plus 1 over 3 to the n minus 1 over 4 to the n plus 1 over 5 to the n minus ... plus ... this is of course the eta function, Euler also studied the related divergent series of the form 1 to the n minus 2 to the n plus 3 to the n minus 4 to the n plus 5 to the n minus ... plus ... Now, some of you might be thinking divergent series. What can you possibly say about divergent series other than that they diverge? But Euler actually discovered a way to assign to these different divergent series a kind of generalized sum. And I'll review that now. I have a whole video on it on my channel, which I encourage you to watch if you're not familiar with this topic. But here's a brief review. So our starting point will be the divergent series 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus ... minus ... This series clearly diverges. It does not approach a limit in any way. Rather, the partial sums of the series oscillate back and forth between 1 and 0. And this is called Grandi's series because that was the mathematician that first wrote about it. And he made the argument that the sort of center of gravity of this series is 1/2. That in a sense, this series could be said to equal 1/2 even though the series diverges. And then Leonhard Euler came along and argued that Grandi's proposal that this series should in some sense be assigned the value 1/2 isn't entirely crazy, because Euler noticed that the function 1 over 1 plus x, which is represented by the alternating geometric series 1 minus x plus x squared minus x cubed plus x to the fourth minus x to the fifth plus ... minus ... over its domain of convergence, its region of convergence, which is x having an absolute value less than 1, then if we evaluate the series at the boundary where it does diverge, in other words, if we set x equal to 1, that's a value for which the series no longer converges, we nonetheless have 1 over 1 plus 1 equals 1 minus 1 to the first plus 1 squared minus 1 cubed plus 1 to the fourth. I should really put that equals in quotation marks here because the series on the right-hand side of the equation does diverge. Nonetheless, the equality would suggest that this series equals 1 over 1 plus 1, or 1/2. So based on this line of argument, Euler claimed that we could reasonably assign the value 1/2 to this divergent series in some generalized sense as the sum of that series. But Euler didn't stop there, because he noticed that if we take this function 1 over 1 plus x, which is equal to the alternating geometric series if the absolute value of x is less than 1, and if we then multiply both sides of this equation by x, we have that x over 1 plus x equals x minus x squared plus x cubed minus x to the fourth plus x to the fifth minus x to the sixth plus x to the seventh minus ... plus ... And then, if we differentiate both sides of the equation, we get 1 over the quantity 1 plus x squared equals 1 minus 2 times x to the first plus 3 times x squared minus 4 times x cubed plus 5 times x to the fourth minus 6 times x to the fifth plus ... minus ... This series representation of the function has the same interval of convergence as the interval of convergence for the alternating geometric series. In other words, it converges for all x whose absolute value is less than 1. So if we then set x equal to 1, we have a divergent series on the right-hand side of the equation, but on the left-hand side, we also have a valid value for that function. So we have setting x equal to 1 here, or in more modern terms, taking the limit as x approaches 1 from the left-hand side, 1 over the quantity 1 plus 1 squared equals, I put that in quotation marks, 1 minus 2 times 1 to the first, plus 3 times 1 squared, minus 4 times 1 cubed, plus 5 times 1 to the fourth, etc., minus dot 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 plus dot dot dot. Well, 1 over the quantity 1 plus 1 squared is 1 over 2 squared, or 1/4, and that is what we would assign to the value of this divergent series. Well, let's carry out this procedure one more time. If we multiply both sides by x and then differentiate, again, this doesn't change the interval of convergence. There are theorems of analysis that prove that fact. Then we have that the function 1 minus x all over the quantity 1 plus x cubed equals 1 minus 2 squared times x plus 3 squared times x squared minus 4 squared times x cubed plus 5 squared times x to the fourth minus 6 squared times x to the fifth plus dot 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 minus dot dot dot. And then if we set x equal to 1, the series on the right-hand side diverges, but we can associate it with the value of the function on the left-hand side of the equation where we set x equal to 1, and we get that 1 minus 1 all over 1 plus 1 quantity cubed equals, in some generalized sense, 1 minus 2 squared times 1 plus 3 squared times 1 squared minus 4 squared times 1 cubed plus 5 squared times 1 to the fourth minus 6 squared times 1 to the fifth plus dot 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 minus dot dot dot. And so something interesting and maybe a little surprising happens here. We find that this divergent series should be assigned the value 0. So we can repeat this process as many times as we want. If we start with the function 1 over 1 plus x and its associated alternating geometric series, and then we multiply that function by x and differentiate, and then take that resulting function, multiply it by x and differentiate, and so on, we get the following list of functions and their associated series that they represent. And these series all converge over the interval absolute value of x is less than 1. Then when we set x equal to 1, these series all diverge at the boundary. However, the functions that represent these series over the interval of convergence do take on finite values, and so we associate those finite values for those functions with their associated divergent series. So here, for completeness sake, I'll just add a few more values to our table. These are the values that we would ascribe to these alternating power series which diverge. I'm going to clean things up one last bit by rewriting that top series 1/2 equals quote-unquote 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus dot 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 minus dot dot dot. Just to maintain consistency with our other series, I'm going to rewrite that as 1/2 equals quote-unquote 1 to the 0 minus 2 to the 0 plus 3 to the 0 minus 4 to the 0 and so on. Well, that's a great technique for assigning a generalized notion of sum to these divergent series, these alternating power series, but one would like to know whether there's an actual formula there. We did find a formula for calculating the sum, and this is an actual sum because these series converge, of the reciprocal powers, and we saw that this formula can be written in terms of the Bernoulli numbers. So if we take eta of 2, for example, which equals 1 over 1 squared minus 1 over 2 squared, plus 1 over 3 squared minus 1 over 4 squared, plus dot 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 minus dot dot dot, we computed this value to equal pi squared over 12. That's what the series actually converges to. And that can be written in the form -1 to the power of 1 minus 1 times b sub 2 times pi squared times the quantity 2 to the second power minus 1 all over 2 factorial. Then when we sub in our value for 1/6 as b sub 2 and make the necessary cancellations, we see that this formula does work. It produces the value pi squared over 12. Similarly, we can use the formula to compute eta of 4, which is 1 over 1 to the fourth minus 1 over 2 to the fourth plus 1 over 3 to the fourth minus 1 over 4 to the fourth plus dot 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 minus dot dot dot. And we find that this equals -1 to the 2 minus 1 times b sub 4 times pi to the fourth times the quantity 2 to the fourth minus 1 all over 4 factorial. And when we sub in our value for b sub 4, that equals -1 over 30. and make the other necessary cancellations, we find, indeed, that eta of 4 equals 7 pi to the 4th over 720. So these infinite series, which are of the form eta of 2n, have a formula that depends explicitly on the Bernoulli numbers, and that formula is eta of 2n equals negative 1 to the n minus 1 times b sub 2n times pi to the 2n times 2 to the 2n minus 1 minus 1 all over 2n factorial. And so Euler asked the perceptive and really interesting question whether the sum of our divergent series that we've already developed so far can also be expressed in terms of a formula involving the Bernoulli numbers. And we'll see that the answer to that question is actually yes. So on our way to solving this, we would want to ask ourselves, is there a formula that we already know about that expresses the sums of powers in terms of the Bernoulli numbers? And the answer to that question, of course, is yes, the Euler-Maclaurin summation formula. And I have an entire video where I give the derivation for this formula on my YouTube channel, but I'll just quickly review what we did there. Recall, please, that the Euler-Maclaurin summation formula, the EMSF for short, was developed by Euler and independently by Maclaurin to find the discrete summation of a function f of x from x equals n back down to x equals 0. Graphically, what that would mean is that if we wanted to find the discrete summation of a function f of x, if we graph that function and then divide the x values up into intervals of 1, and then we form rectangles, each rectangle having a base of 1, and then a height equal to f of x, so our first rectangle would have a height f of 1, the next rectangle would have a height f of 2, and we sum up the areas of all those rectangles, that area would equal the discrete summation of the values of f of x at x equals 1, and x equals 2, and x equals 3, all the way up to x equals n. So we can write that summation more concisely as the sum of f of k from k equals 1 to n, and Euler found, well, that summation depends on our choice of n. It's actually a function of n, and so he was able to derive a formula for that summation purely in terms of f of x, its integral, and its derivatives of all orders, and this summation formula is intimately connected to the Bernoulli numbers. Namely, Euler found that the summation of f of k from k equals 1 to n is equal to the integral of f of x dx minus b sub 1, the first Bernoulli number, over 1 factorial times f of n, plus b sub 2 over 2 factorial times f prime of n, plus b sub 4 over 4 factorial times f triple prime of n, plus b sub 6 over 6 factorial times the fifth derivative of f evaluated at n, plus dot dot dot. Now note that this formula, as Euler derived it, is an infinite summation. In practice, we would like to truncate the summation somewhere and have a remainder term that bounds the error, that tells us how far off our summation formula is from the actual discrete summation of the function from k equals 1 to n. Well, Euler never discovered that error term, and it wasn't actually discovered until about 100 years later by Poisson, but we won't need an error term for our purposes in this video today. But even without an error term, Euler was able to revise and generalize this formula to compute the discrete summation of a function f of x from x equals n to infinity over some arbitrary interval. And I have a separate video in my channel where I show how Euler did that. Graphically, what that means is that if we have some function f of x and we want to sum its values on x equals n, and then on x equals n plus h, and then x equals n plus 2h, and so on up to infinity, we're summing the areas of these rectangles. The first one is based at n, the next one is based at n plus h, the one after that at n plus 2h, and each rectangle has a height that corresponds to that x value. So the first one has a height f of n, the next one has a height f of n plus h, and of course each rectangle has a width of 1. So we're summing the areas of these rectangles with base width 1 and height f of n plus h, f of n plus 2h, and so on. And Euler found the formula for this discrete summation that sums f of n plus kh from k equals 0 to infinity, that this discrete summation equals the following. Well, first just let me substitute x for n here. And then once we do that, we have that this summation equals negative 1 over h times the integral of f of x dx minus b sub 1 over 1 factorial times f of x minus b sub 2 over 2 factorial times h times f prime of x minus b4 over 4 factorial times h cubed times f triple prime of x minus b6 over 6 factorial times h to the fifth times the fifth derivative of f evaluated at x minus b sub 8 over 8 factorial times h to the seventh times the seventh derivative of f evaluated at x minus dot dot dot. And just to make things a little more explicit, I'll list these first several Bernoulli numbers, and it's not of any consequence now that I'm using a lowercase b instead of a capital B, just in case anyone's confused about that. So we have b sub 1 equals negative 1/2, b sub 2 equals 1/6, and then I'll skip b sub 3, that equals 0. In fact, all the odd indexed Bernoulli numbers after b sub 1 equals 0. So then we have b sub 4 equals negative 1 over 30, b sub 6 equals 1 over 42, b sub 8 equals negative 1 over 30 again, and so on. So then when we substitute in our values for the Bernoulli numbers, we get this formula, which is the alternative form of the EMSF, which I derived in my previous video. So starting with this more general form of the Euler-Maclaurin summation formula, Euler realized that it could be adapted even further to give him the sum of an alternating series. And here's how he did that. If we take the EMSF that sums a function from some value x to infinity over some arbitrary interval h, first if we substitute 2h for h, in other words, if we double the length of the interval, we get that f of x plus f of x plus 2h plus f of x plus 4h plus f of x plus 6h plus dot 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 equals negative 1 over 2h times the integral of f of x dx, and then the next term is unchanged because it doesn't have any h in it, so plus 1/2 f of x minus 1 over 2 factorial times 1 over 6 times 2h times f prime of x plus 1 over 4 factorial times 1 over 30 times 2 cubed h cubed times f triple prime of x minus 1 over 6 factorial times 1 over 42 times 2 to the fifth times h to the fifth times the fifth derivative of f evaluated x plus dot 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 minus dot dot dot. Next, we multiply the bottom equation by 2, and we get 2 times f of x plus 2 times f of x plus 2h plus 2 times f of x plus 4h plus 2 times f of x plus 6h plus dot 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 equals 2 times negative 1 over 2h times the integral of f of x dx plus 2 times 1/2 times f of x minus 2 times 1 over 2 factorial times 1/6 times 2h times f prime of x, and so on. So the 2's cancel in the first and second terms on the right-hand side, and then multiplying all the subsequent terms by 2 just raises the exponent, so 2h becomes 2 squared h, 2 cubed times h cubed becomes 2 to the 4th times h cubed, and I didn't write 2 to the 6th times h to the 5th for the last one, but we'll catch up on that one later. And so finally, to produce the alternating series, which is why we've performed these mathematical operations in the first place, we subtract the second equation from the first equation. And so when we do that, on the left-hand side of the equation, we'll have negative f of x, and then the plus f of x plus h term is untouched. And then we have f of x plus 2h minus 2 times f of x plus 2h. That gives us a minus f of x plus 2h. Then the f of x plus 3h term, again, is unaffected. And then we have, it's not written here, but we can see that we'd have plus f of x plus 4h minus 2 times f of x plus 4h, which will give us a minus f of x plus 4h, and so on. So we have our alternating series on the left-hand side now. Now, what would this alternating series equal? Well, we notice that when we perform the subtraction, the terms involving the integral of f of x cancel each other out. Well, that's very nice. Then we have the term plus 1/2 times f of x, now minus 1 times f of x, so that gives us a minus 1/2 times f of x. When I subtract the next two terms from each other, note that because I have a double negative with the second equation, I'm doing minus 1 over 2 factorial times 1/6 times 2 squared h times f prime of x. That actually becomes a positive. So I end up with this equaling, when I simplify, 1 over 2 factorial times 1/6 times the quantity 2 squared minus 1, close parenthesis, times h times f prime of x. The term after that, when I do the subtraction, I get minus 1 over 4 factorial times 1 over 30 times the quantity 2 to the 4th minus 1, close parenthesis, times h cubed times f triple prime of x. And then the next term after that, again because of the double negative sign, would be plus 1 over 6 factorial times 1 over 42 times the quantity 2 to the 6th minus 1, close parenthesis, times h to the 5th times the 5th derivative of f of x. And then it will be minus dot 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 plus dot dot dot, following that same pattern. Now this equation is pretty close to what we want, but we wanted f of x minus f of x plus h plus f of x plus 2h minus f of x plus 3h, and so on. So all we have to do to get that result is multiply both sides of the equation by -1 to flip the signs. And now finally, because our choice of h is arbitrary, we can let h equal 1. Then we'll have the final form that we seek. F of x minus f of x plus 1 plus f of x plus 2 minus f of x plus 3 plus f of x plus 4 minus f of x plus 5 plus dot 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 minus dot 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 equals 1/2 times f of x minus 1 over 2 factorial times 1/6 times 2 squared minus 1 times f prime of x plus 1 over 4 factorial times 1 over 30 times the quantity 2 to the 4th minus 1 times f triple prime of x minus 1 over 6 factorial times 1 over 42 times 2 to the 6th minus 1 times the 5th derivative of f of x plus dot 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 minus dot dot dot. And now we're really in business, everyone, because we can use this version of the EMSF to compute the generalized sums of our divergent series in terms of the Bernoulli numbers. So I'll bring that formula to the top here, and I'll just add one more term, that last term there, 1 over 8 factorial times 1 over 30 times 2 to the 8th minus 1 times the 7th derivative of f of x minus dot 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 plus dot dot dot. And now let's try the simplest possible case. We'll let f of x equal x to the first. Then we'll have f of x, x to the first, minus f of x plus 1, so that's going to be the quantity x plus 1 to the first, plus f of x plus 2, that's going to be x plus 2 to the first, minus x plus 3 to the first, plus x plus 4 to the first, minus x plus 5 to the first, plus dot 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 minus dot 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 equals 1/2 times f of x, so that's 1/2 times x to the first, minus 1 over 2 factorial times 1 over 6 times the quantity 2 squared minus 1 times f prime of x. Well, f prime of x is just going to equal 1 times x to the 0, which just equals 1. And in fact, all the subsequent higher order derivatives of f of x are just all going to equal 0. So next I would have plus 1 over 4 factorial times 1 over 30 times the quantity 2 to the 4th minus 1 times 0. And in fact, all the other terms will be multiplying 0, so then it will be minus a lot of stuff times 0, so minus 0, plus a lot of stuff times 0, so plus 0, so it'll be minus 0, plus 0, minus 0, plus 0, and so on. So all the terms after the first two terms in the right-hand side of the equation just cancel because they all equal 0. And now, because we're completely free in our choice of x, we can let x equal 0. And then we'll have on the left-hand side, letting x equal 0, -1 to the first, plus 2 to the first, minus 3 to the first, plus 4 to the first, minus 5 to the first, plus dot dot dot, minus dot dot dot, equals, and now on the right-hand side, that first term, 1/2 times 0 to the first, that just cancels away, and we're left with the right-hand side being minus 1 over 2 factorial times 1 over 6 times the quantity 2 squared minus 1 times 1. So this just equals minus 1 over 2 factorial, or minus 1 over 2, times 1/6 times 3 times 1, which equals -3 over 12, or -1/4. Now to get the result we seek, we just have to multiply both sides of the equation by -1, and then we find that 1 to the first minus 2 to the first, plus 3 to the first, minus 4 to the first, plus 5 to the first, minus dot dot dot, plus dot dot dot, equals 1/4. So amazingly, we've arrived at the same result for the quote-unquote sum of this divergent series, but by a completely different methodology. Remember that when we first approached this problem, we considered the function 1 over the quantity 1 plus x squared, which is represented in the region where the absolute value of x is less than 1 by the series 1 minus 2 times x to the first plus 3 times x squared minus 4x cubed plus 5x to the fourth minus dot 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 plus dot dot dot. Then we set x equal to 1 to have 1 over 1 plus 1 quantity squared equals, and here I should put equals in quotes because now the series diverges, equals, quote unquote, 1 minus 2 times 1 to the first plus 3 times 1 to the second power minus 4 times 1 cubed plus 5 times 1 to the fourth minus dot 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 plus dot dot dot, which reduces to the statement 1/4 equals, quote unquote, 1 minus 2 plus 3 minus 4 plus 5 minus dot 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 plus dot dot dot. So this is pretty awesome. We derived the same result for this divergent series by two completely different methods. But perhaps more importantly, now we see how the value 1/4, which is associated with this divergent series, actually depends on the Bernoulli numbers. So to make that relationship more explicit, I'm going to write 1 to the first minus 2 to the first plus 3 to the first minus 4 to the first plus 5 to the first minus dot 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 plus dot 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 equals 1 over 2 factorial times, and now in place of 1/6, I'll write b sub 2, the second Bernoulli number, times the quantity 2 squared minus 1 close parenthesis. Well, let's do another one. Let's try this method for f of x equals x squared. And let's work on in advance this time what the derivatives would be. F prime of x equals 2x, f double prime of x equals 2, and then f triple prime of x equals 0, and in fact all the subsequent higher order derivatives of f equals 0. They all equal 0 from f triple prime of x onward. So then we have x squared minus the quantity x plus 1 squared plus the quantity x plus 2 squared minus the quantity x plus 3 squared plus x plus 4 squared minus x plus 5 squared plus dot 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 minus dot 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 equals 1/2 times f of x, so 1/2 times x squared, minus 1 over 2 factorial times 1/6 times the quantity 2 squared minus 1 times f prime of x, so times 2x, plus 1 over 4 factorial times 1 over 30 times the quantity 2 to the fourth minus 1 times f triple prime of x, which actually just equals 0. And in fact, all the subsequent terms also multiply 0 because all the higher order derivatives of f equals 0. So we have minus 0 plus 0 minus 0 plus 0 and so on. So I'll just erase those 0 entries. So now we know what to do. We set x equal to 0, and we get 0 squared minus the quantity 0 plus 1 squared plus the quantity 0 plus 2 squared minus 0 plus 3 squared plus 0 plus 4 squared minus 0 plus 5 squared plus dot 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 minus dot 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 equals 1/2 times 0 squared minus 1 over 2 factorial times 1 over 6 times 2 squared minus 1 times 2 times 0. And so when we set x equal to 0 for this equation, it actually cancels out all the terms on the right-hand side. And so we have minus 1 squared plus 2 squared minus 3 squared plus 4 squared minus 5 squared plus dot 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 minus dot 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 equals 0. And so now when we multiply both sides by -1, we then have 1 squared minus 2 squared plus 3 squared minus 4 squared plus 5 squared minus dot 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 plus dot 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 equals 0. And this is exactly what we found before for this particular divergent series. So in order to see still more clearly what's going on here, let's try f of x equals x cubed. And then for our derivatives, we'll have f prime of x equals 3x squared, f double prime of x equals 3 times 2 times x to the first, f triple prime of x equals 3 factorial times x to the 0, which of course is just 3 factorial, and that's a constant, so when we differentiate further, we're going to have f quadruple prime of x equals 0, and all subsequent higher order derivatives of f of x are going to equal 0. Great, so when we plug in f of x equals x cubed into our equation, on the left-hand side we have x cubed minus the quantity x plus 1 cubed plus the quantity x plus 2 cubed minus x plus 3 cubed plus x plus 4 cubed minus x plus 5 cubed plus dot 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 minus dot 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 equals 1/2 times f of x, so 1/2 x cubed, minus 1 over 2 factorial times 1/6 times the quantity 2 squared minus 1 times f prime of x, which is times 3x squared, plus 1 over 4 factorial times 1 over 30 times the quantity 2 to the fourth minus 1 times f triple prime of x, which is just 3 factorial, minus 1 over 6 factorial times 1 over 42 times the quantity 2 to the sixth minus 1 times the fifth derivative of f of x, which is just 0. And then all the other terms also multiply higher order derivatives of f of x, which all equal 0. So we just have then plus 0, minus 0, plus 0, minus 0, and so on. So all those 0 terms cancel on the right-hand side. And then we know the procedure. We let x equal 0. And then we have 0 cubed minus the quantity 0 plus 1 cubed, plus the quantity 0 plus 2 cubed, minus 0 plus 3 cubed, plus 0 plus 4 cubed, minus 0 plus 5 cubed, plus dot dot dot, minus dot dot dot, equals 1/2 times 0 cubed minus 1 over 2 factorial times 1/6 times the quantity 2 squared minus 1 times 3 times 0 squared plus 1 over 4 factorial times 1 over 30 times 2 to the 4th minus 1 times 3 factorial. And now those first two terms on the right-hand side cancel out because they multiply 0. And the only term that actually survives cancellation on the right-hand side is this expression 1 over 4 factorial times 1 over 30 times 2 to the 4th minus 1 times 3 factorial. So now we know what to do. We'll multiply both sides of the equation by -1 to produce the series 1 cubed minus 2 cubed plus 3 cubed minus 4 cubed plus 5 cubed minus dot 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 plus dot 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 equals minus 1 over 4 factorial times 1 over 30 times the quantity 2 to the 4th minus 1 times 3 factorial. Well, I'll just bring that 3 factorial all the way over. This will equal minus 3 times 2 times 1 over 4 times 3 times 2 times 1 times 1 over 30 times, well, 2 to the 4th is 16, so times 16 minus 1, which is just 15. And after I cancel some terms in the numerator and the denominator, I have that this equals negative 15 over 4 times 30, or negative 15 over 120, which equals negative 1/8, which is exactly what we found to be the value assigned to this divergent series by our other method. But remember, negative 1 over 30 is the fourth Bernoulli number, b sub 4. So if I wanted to put this expression purely just in terms of the Bernoulli numbers, I would write this as 3 factorial times b sub 4 over 4 factorial times the quantity 2 to the 4th minus 1. Now I think if we work through one last example, the pattern will become very clear. So let's let f of x now equal x to the 4th. And then our derivatives will be f prime of x equals 4 times x cubed. F double prime of x will be 4 times 3 times x squared. F triple prime of x will be 4 times 3 times 2 times x to the first. And f quadruple prime of x will be 4 times 3 times 2 times 1 times x to the 0, which of course is just 4 factorial, a constant. And so then the fifth derivative of f and the sixth derivative and all the subsequent higher order derivatives will equal 0. Okay, so when we plug in x to the 4th for f of x into the above equation, we have x to the 4th minus the quantity x plus 1 to the 4th plus the quantity x plus 2 to the 4th minus x plus 3 to the 4th plus x plus 4 to the 4th minus x plus 5 to the 4th plus dot 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 minus dot 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 equals 1/2 times x to the 4th minus 1 over 2 factorial times 1 over 6 times the quantity 2 squared minus 1 times 4x cubed plus 1 over 4 factorial times 1 over 30 times the quantity 2 to the 4th minus 1 times 4 times 3 times 2 times x to the 1st minus 1 over 6 factorial times 1 over 42 times the quantity 2 to the 6th minus 1 times the fifth derivative of f of x, which equals 0 here, and then all the other terms multiply 0, so then it will be plus 0, minus 0, plus 0, minus 0, and so on. So all those 0 terms drop out, and then when we set x equal to 0, we have 0 to the 4th minus the quantity 0 plus 1 to the 4th, plus the quantity 0 plus 2 to the 4th, minus 0 plus 3 to the 4th, plus 0 plus 4 to the 4th, minus 0 plus 5 to the 4th, plus dot dot dot, minus dot 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 on the left-hand side. And on the right-hand side, all of our surviving terms multiply x raised to some exponent. So when we set x equal to 0, those terms also drop out. So the right-hand side of this equation equals 0. And when we multiply both sides of the equation by -1, we flip the signs on the left-hand side. So we have 1 to the 4th minus 2 to the 4th plus 3 to the 4th minus 4 to the 4th plus 5 to the 4th minus dot 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 plus dot 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 equals 0. And this is exactly what we computed for this series by our other method. So hopefully after working through those 4 examples, we have a good enough sense of what's going on, because I'd like to generalize now. But I'm going to start by just considering this formula and noticing that this formula only includes the odd derivatives of f of x, f prime of x, f triple prime of x, the fifth derivative, the seventh derivative, and so on. And I would like to include the even derivatives also, but just as void entries, because there are no even derivatives of f of x in this equation. I'm just going to include them all multiplying 0. So that will change the form of the equation without actually changing any of its content. So we'll have that this equals, on the right-hand side, 1/2 times f of x minus 1 over 2 factorial times b sub 2 times 2 squared minus 1 times f prime of x, but then I'll include the f double prime term. So that'll be plus 0 times f double prime of x, then minus 1 over 4 factorial times b sub 4 times 2 to the fourth minus 1 times f triple prime of x, and then plus 0 times f quadruple prime of x, and so on. So the even derivatives of f of x I'll multiply 0, but this will help us see what's going on here. And then to consider this in full generality, we'll let f of x equal x to the n. And then we'll notice that f prime of x equals n times x to the n minus 1. F double prime of x equals n times n minus 1 times x to the n minus 2. F triple prime of x equals n times n minus 1 times n minus 2 times x to the n minus 3, and so on until we get to the nth derivative of f of x. So fn of x will equal n factorial, which of course is a constant. And then after that, all subsequent higher order derivatives will all equal 0. So if we start by considering the situation where n is an odd integer, if n is odd, then the last term in our series on the right-hand side of this expression would be negative 1 over n plus 1 factorial times b sub n plus 1 times 2 to the n plus 1 minus 1 times the nth derivative of f of x, fn of x, which is just n factorial. Then when we set x equal to 0, we have negative 1 to the n plus 2 to the n minus 3 to the n plus 4 to the n minus 5 to the n plus dot 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 minus dot 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 equals 1/2 times 0 to the n minus 1 over 2 factorial times b sub 2 times 2 to the second minus 1 times n times 0 to the n minus 1 plus 0 times f double prime of x minus 1 over 4 factorial times b sub 4 times 2 to the fourth minus 1 times n minus 1 times 0 to the n minus 1, and so on. And so all of our terms on the right-hand side cancel except for our very last term in the series, and we're left with the expression negative 1 to the n plus 2 to the n minus 3 to the n plus 4 to the n minus 5 to the n plus dot 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 minus dot 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 equals negative 1 over n plus 1 factorial times b sub n plus 1 times 2 to the n plus 1 minus 1 times n factorial. Then when we multiply both sides of the equation by negative 1, we get the final form that we want. 1 to the n minus 2 to the n plus 3 to the n minus 4 to the n plus 5 to the n minus dot 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 plus dot 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 equals n factorial over n plus 1 factorial times b sub n plus 1 times the quantity 2 to the n plus 1 minus 1. So I'll put a box around that. That's our final expression for the alternating power series with odd exponents in terms of the Bernoulli numbers. And now it should be clear to us why, if we make n an even positive integer, our alternating power series, even though it diverges, is always assigned a value of 0. And the reason for that is that all the terms on the right-hand side of the equation, except for maybe the very last term, cancel out because they consist of a bunch of coefficients multiplying x to some exponent, or they're just void entries to begin with. And then when we go to the very last term, if n is an even integer, that last term is going to be one of our void entries. It's going to be an even derivative of f of x, so it could be f8 of x, f10 of x, f12 of x, whatever. But that's always going to be multiplying a 0 because the right-hand side of the equation only has void entries for the even derivatives of f of x. So it will be 0 times fn of x, which would be 0 times n factorial, which also just equals 0. So finally, we end up with an equation of the form negative 1 to the n plus 2 to the n minus 3 to the n plus 4 to the n minus 5 to the n plus dot 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 minus dot 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 equals 0. And then when we multiply both sides of the equation by negative 1, we get our final form, if n is even, 1 to the n minus 2 to the n plus 3 to the n minus 4 to the n plus 5 to the n minus dot 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 plus dot 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 equals 0. So now we have a way of writing our generalized sums for these divergent series purely in terms of the Bernoulli numbers. We have, for example, that our very first series, 1 to the first minus 2 to the first plus 3 to the first minus 4 to the first and so on, to which we assigned the value 1/4, we found that 1/4 is actually 1 factorial times b sub 2 over 2 factorial times the quantity 2 squared minus 1. Our next alternating divergent series was assigned a value of 0. And the one after that, 1 cubed minus 2 cubed plus 3 cubed minus 4 cubed, etc., was assigned a value of negative 1/8, which by our formula is found to equal 3 factorial times b sub 4 over 4 factorial times 2 to the 4th minus 1, and so on. So the pattern continues, and we're able to assign to all of the divergent series of this form a generalized sum, which can be expressed in terms of a formula involving the Bernoulli numbers. And this is where things get really interesting, because remember that we already determined a formula for the eta function, which represents the alternating sums of the reciprocals of powers, in terms of the Bernoulli numbers. Specifically, we found that eta of 2n equals negative 1 to the n minus 1 times b sub 2n times pi to the 2n times the quantity 2 to the 2n minus 1 minus 1, close parenthesis, all over 2n factorial. So then we have, for example, letting n equal 1 and 2n equaling 2, eta of 2 will be negative 1 to the 1 minus 1 times b sub 2 times pi squared times 2 to the second power minus 1 minus 1, close parenthesis, all over 2 factorial, letting n equal 2 and 2n equaling 4. Eta of 4 will equal negative 1 to the 2 minus 1 times b sub 4 times pi to the 4th times the quantity 2 to the 4th minus 1 minus 1, all over 4 factorial. And then, of course, eta of 2 is just 1 over 1 squared minus 1 over 2 squared plus 1 over 3 squared minus 1 over 4 squared plus 1 over 5 squared minus ... plus ... And eta of 4 is just 1 over 1 to the 4th minus 1 over 2 to the 4th plus 1 over 3 to the 4th minus 1 over 4 to the 4th plus 1 over 5 to the 4th minus ... plus ... So this leads us to a natural question. Is there some relationship between the sums of our series of the type 1 over 1 to the n minus 1 over 2 to the n plus 1 over 3 to the n minus 1 over 4 to the n plus 1 over 5 to the n minus 1 over 6 to the n plus ... minus ... which of course is the eta function, and the generalized sums of the divergent series 1 to the n minus 2 to the n plus 3 to the n minus 4 to the n plus 5 to the n minus 6 to the n plus ... minus ... And the answer to that question, amazingly, is yes. And this relationship is the Eta Functional Equation. Because now that we've discovered a formula for the generalized sums of these divergent alternating sums of power series, purely in terms of the Bernoulli numbers, and we've also discovered a related formula for the alternating sums of reciprocal powers, the Eta function, then we might be tempted to sort of line these equations up together and see what we can cancel. More concretely, we can look at the divergent series 1 to the first minus 2 to the first plus 3 to the first minus 4 to the first plus 5 to the first minus ... plus ... That has a generalized sum which is dependent on the Bernoulli number b sub 2. And we can divide that expression by the eta function of 2, 1 over 1 squared minus 1 over 2 squared plus 1 over 3 squared minus 1 over 4 squared plus 1 over 5 squared minus ... plus ... which actually converges to a sum whose formula also depends on b sub 2. By the same token, the divergent series 1 cubed minus 2 cubed plus 3 cubed minus 4 cubed plus 5 cubed minus ... plus ... has a generalized sum that depends on the Bernoulli number b sub 4, and we can divide that expression by eta of 4, 1 over 1 to the 4th minus 1 over 2 to the 4th plus 1 over 3 to the 4th minus 1 over 4 to the 4th plus 1 over 5 to the 4th minus ... plus ... which converges to a sum that also depends on b sub 4. And we can keep going. We can take the divergent series 1 to the 5th minus 2 to the 5th plus 3 to the 5th minus 4 to the 5th plus 5 to the 5th minus ... plus ... whose generalized sum depends on the 6th Bernoulli number b sub 6, and we can divide that expression by eta of 6, whose sum also depends on b sub 6. And now look what happens when we do that. The Bernoulli numbers cancel as well as the factorial terms that divide them. So b sub 2 over 2 factorial, those terms cancel. B sub 4 over 4 factorial, those terms cancel from the numerator and the denominator. And b sub 6 over 6 factorial, those terms cancel from that quotient. So when we cancel out those terms, we get that the first quotient, 1 to the first minus 2 to the first plus 3 to the first minus 4 to the first, etc., over eta of 2 equals 1 factorial times the quantity 2 squared minus 1 all over pi squared times the quantity 2 to the first minus 1. 1 cubed minus 2 cubed plus 3 cubed minus 4 cubed, and so on, all over eta of 4 equals negative 3 factorial times 2 to the fourth minus 1 all over pi to the fourth times the quantity 2 cubed minus 1. 1 to the fifth minus 2 to the fifth plus 3 to the fifth minus 4 to the fifth, and so on, all over eta of 6 equals 5 factorial times the quantity 2 to the sixth minus 1 all over pi to the sixth times the quantity 2 to the fifth minus 1. But we can fill out this pattern by adding a few more expressions to the list here. For example, I could have included 1 squared minus 2 squared plus 3 squared minus 4 squared plus 5 squared minus plus all over eta of 3, which is 1 over 1 cubed minus 1 over 2 cubed plus 1 over 3 cubed minus 1 over 4 cubed plus 1 over 5 cubed. Now, I don't have a formula for what eta of 3 equals, but by the alternating series test, I know it converges to some positive number. Meanwhile, the value that we assigned to 1 squared minus 2 squared plus 3 squared minus 4 squared and so on is 0. So this quotient is 0 over something. It's not a 0 over 0 expression, so the entire thing just reduces to 0. Next, I could add 1 to the fourth minus 2 to the fourth plus 3 to the fourth minus 4 to the fourth plus 5 to the fourth minus plus . That's another divergent series to which we assign the value 0. And we can divide this by eta of 5, 1 over 1 to the fifth minus 1 over 2 to the fifth plus 1 over 3 to the fifth minus 1 over 4 to the fifth plus 1 over 5 to the fifth minus plus . Again, I don't know what eta of 5 equals, but by the alternating series test, I know it converges, again, to some positive number. So this is, again, a 0 expression. Now I'm going to take this equation on the bottom of the page and bring it to the top so you can see how this pattern continues. After our series 1 to the fifth minus 2 to the fifth plus 3 to the fifth and so on all over eta of 6, I want to write out the quotient of 1 to the sixth minus 2 to the sixth plus 3 to the sixth minus 4 to the sixth plus 5 to the sixth minus plus . And I'm going to divide that by eta of 7. Well, once again, our numerator is a divergent series to which we assign the value 0. And the denominator converges to some value, so this is 0 over some finite value, so the entire expression equals 0. Next, we would have 1 to the seventh minus 2 to the seventh plus 3 to the seventh minus 4 to the seventh plus 5 to the seventh minus plus all over eta of 8, and this will equal 7 factorial times b sub 8 over 8 factorial times 2 to the 8th minus 1 all over negative 1 to the 4 minus 1 times b sub 8 times pi to the 8th times 2 to the 7th minus 1 close parenthesis all over 8 factorial. And then the b sub 8 over 8 factorial terms cancel, and we're left with this equaling negative 7 factorial times 2 to the 8th minus 1 close parenthesis all over pi to the 8th times 2 to the 7th minus 1. As you can probably guess, our next series, 1 to the 8th minus 2 to the 8th plus 3 to the 8th minus 4 to the 8th plus 5 to the 8th minus plus all over eta of 9, again, is 0 over some finite convergent sum, so this equals 0 again. And now we might notice an interesting periodicity here. So we've taken the quotient of 8 pairs of series so far, and here are the first 4 of them. And if we look, the first one's positive, the second one is 0, the next one after that is negative, and then the fourth one is 0 again. So if I were to attach a coefficient to each of these quotients, the most obvious choice would be 1, 0, negative 1, 0. And then if I look at the next set of 4 quotients, again, we see that the fifth one is positive. This is the fifth because this is like page 2 here, guys. The next one is 0. The one after that is negative, and the one after that is 0 again. So again, it would be 1, 0, negative 1, 0. Well, it almost feels as if concealed within this formula for the quotients of these series is some function that has this periodicity property. And so we'd like to model that periodic behavior with a function. Well, we could let this function that's generating the coefficients depend on either the exponent in the numerator or the denominator. Euler went with the denominator, probably just after some trial and error and seeing that things work out really beautifully if we do that. Well, the series in all of our denominators here are just the eta function. For example, our first denominator is eta of 2, and eta of 2 gives us 1 over 1 squared minus 1 over 2 squared plus 1 over 3 squared and so on, which is the same as saying 1 to the negative 2 minus 2 to the negative 2 plus 3 to the negative 2 and so on. So let's just negate that exponent to get back positive 2 as the argument for this function generating the coefficient. And we'll do that for all of our denominators. So the next pairing where we have eta of 3 in the denominator, we'll just let n equal 3, and then we'll let n equal 4 for the pair that has eta of 4 in the denominator, and so on and so forth. So if c of n is the function giving us the coefficient multiplying each of our quotients of series, we would have for n equals 2, c of n equals 1. For n equals 3, c of n equals 0. For n equals 4, c of n equals negative 1. For n equals 5, c of n equals 0. And then the pattern repeats. Well, let's graph this function. For n equals 2, we have c of n equals 1. For n equals 3, c of n equals 0. For n equals 4, c of n equals negative 1. For n equals 5, c of n equals 0 again, and so on. Well, what function could c of n be? If we connect the dots, it becomes pretty clear that it's something sinusoidal. And now extrapolating, I'll just extend the function back a little bit to where it intersects the y-axis. And now if we look at this function, it appears to be the negative of a cosine wave. A cosine wave with period 4. So this function is negative cosine n pi over 2, close parenthesis. So let's go back to our quotients of infinite series and make use of that information. So here I've just written out the infinite series quotients where we have a non-zero result. So our first one is 1 to the first minus 2 to the first plus 3 to the first minus 4 to the first and so on, all over eta of 2. The next one where we have a non-zero result is 1 cubed minus 2 cubed plus 3 cubed minus 4 cubed and so on, all over eta of 4. And then we have the series with 1 to the 5th minus 2 to the 5th and so on over eta of 6, and then 1 to the 7th minus 2 to the 7th plus 3 to the 7th and so on all over eta of 8. And we can see that these quotients alternate from positive to negative. So the coefficient of the first one will be positive 1, the coefficient of the one below that is negative 1, the coefficient of the third line there is positive 1, and then negative 1 again for the last line. But we know now that this behavior is modeled by negative cosine of n pi over 2. So for this first top line where n equals 2, in place of 1 I can write negative cosine 2 pi over 2. Cosine pi, of course, is negative 1, so negative cosine pi is positive 1. For the next one where n equals 4, I can write negative cosine 4 pi over 2. Cosine of 4 pi over 2 equals cosine 2 pi, which is just 1, so negative cosine 4 pi over 2 is negative 1. And so on, the next leading coefficient will be negative cosine 6 pi over 2, and the last one will be negative cosine 8 pi over 2. And now I want to just point out another pattern that's occurring here, which is that we have a factorial in the numerator of each of these results for these non-zero quotients of our infinite series. For our n equals 2 case, we have a 1 factorial in the numerator. For n equals 4, we have a 3 factorial. For n equals 6, we have a 5 factorial in the numerator. And for n equals 8, we have a 7 factorial. And for those of you who have been watching this channel for a long time, you may know that we've done a lot of videos on the gamma function. And the gamma function is this amazing function that extends the concept of the factorial to non-integer inputs, and by definition, gamma of n equals n minus 1 factorial. So in place of 1 factorial for the n equals 2 case, I'm going to write gamma of 2. In place of 3 factorial for the n equals 4 case, I'm going to write gamma of 4. In place of 5 factorial for the n equals 6 case, I'm going to write gamma of 6. And in place of 7 factorial for the n equals 8 case, I'm going to write gamma of 8. Well, that's really cool, but there's more. So far, I've only written the denominators of these quotients in terms of the eta function. But what about the numerators? Well, let's consider, for example, our first case. 1 to the first minus 2 to the first plus 3 to the first minus 4 to the first plus 5 to the first minus ... plus ... This is the same as writing, although we never do this, it makes sense to do it here, 1 to the negative negative 1 minus 2 to the negative negative 1 plus 3 to the negative negative 1 minus 4 to the negative negative 1 plus 5 to the negative negative 1 minus dot 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 plus dot dot dot. In fact, we could do this in general. We would have 1 to the k minus 2 to the k plus 3 to the k minus 4 to the k plus 5 to the k minus dot 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 plus dot 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 is equivalent to 1 to the negative negative k minus 2 to the negative negative k plus 3 to the negative negative k, and so on. And so what does the series 1 to the k minus 2 to the k plus 3 to the k minus 4 to the k and so on equal? It just equals eta of negative k. And so with that insight in mind, I can rewrite the numerators of all of these quotients in terms of the eta function again. I can write the top line as eta of negative 1 over eta of 2. The next quotient will be eta of negative 3 over eta of 4. The one below that will be eta of negative 5 over eta of 6. And the last one here will be eta of negative 7 over eta of 8. But remember that everything on the right-hand side of these equations is written in terms of the denominator. In the first case, n equals 2, in the next case n equals 4, in the third case n equals 6, and in the last case n equals 8. So I would like to write my numerators also in terms of n. So instead of writing eta of negative 1 for the top numerator, I'm going to write eta of 1 minus 2, because negative 1 is 1 minus 2. The next one, instead of writing eta of negative 3, I'm going to write eta of 1 minus 4, because 1 minus 4 is negative 3. And then in the third quotient here, where n equals 6, instead of writing eta of negative 5 in the numerator, I'll write eta of 1 minus 6. And then in the last quotient, instead of eta of negative 7, I'll write eta of 1 minus 8. And with that change in place, Euler came to the startling realization that he had hit upon a functional equation for the eta function. Specifically, Euler surmised that eta of 1 minus n over eta of n equals negative cosine of n pi over 2 times gamma of n times the quantity 2 to the n minus 1 all over pi to the n times the quantity 2 to the n minus 1 minus 1 close parenthesis. This is the Eta Functional Equation, and I'm going to put a big box around it because it's such an important result. Well, what do I mean by functional equation? A functional equation is an equation that relates the values that a function takes on one set of inputs to the value that same function takes on a different set of inputs. So here, if I know eta of n, I can use this equation to compute eta of 1 minus n, and vice versa. Well, how general is this formula? So far, we've derived it by looking at series that can be written purely in terms of the Bernoulli numbers, but that leaves out a very important series that's of the same type that does not have an expression that we know of in terms of Bernoulli numbers, namely 1 over 1 to the first minus 1 over 2 to the first plus 1 over 3 to the first minus 1 over 4 to the first plus 1 over 5 to the first minus dot 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 plus dot dot dot. We know that that series converges to the natural logarithm of 2. In fact, this is the alternating harmonic series. Well, to test the generality of our eta functional equation, I'm going to form a quotient using eta of 1 here. Eta of 1, of course, is our alternating harmonic series, and it's equal to natural log of 2. I'll put eta of 1 in the denominator of this quotient, and in the numerator, I'll have eta of 1 minus 1, or just eta of 0. So eta of 0 is 1 over 1 to the 0 minus 1 over 2 to the 0 plus 1 over 3 to the 0 minus 1 over 4 to the 0 plus 1 over 5 to the 0 minus dot 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 plus dot dot dot. That's of course 1 over 1 minus 1 over 1 plus 1 over 1 minus 1 over 1, or just 1 minus 1 plus 1 minus 1 plus 1 and so on. That's Grandi's series, to which we know to assign a value of 1/2. Now the work that we've done already on both of these series would imply that eta of 0 divided by eta of 1 would equal 1/2 over log 2, which simplifies to 1 over 2 log 2. Now we need to check whether our eta functional equation gives us the same result. Now remember, we derived our eta functional equation only using series that could be expressed in terms of Bernoulli numbers, but I don't have a general method of expressing either of these two series in terms of Bernoulli numbers. So we need to check whether the eta functional equation works here. In particular, we're asking for n equals 1, does negative cosine of 1 pi over 2, close parenthesis, times gamma of 1, times the quantity 2 to the first power minus 1, close parenthesis, all over pi to the 1 times the quantity 2 to the 1 minus 1, close parenthesis, equal 1 over 2 log 2. So I'll just bring this equation to the top line here. We want to see if the expression on the left-hand side is equal to 1 over 2 log 2. So I just want to rearrange the terms a little bit here. It'll make it clearer what's going on. So first I'll write cosine 1 pi over 2, and then for that negative sign, I'll just put a negative 1 in the product there, and then this is going to multiply gamma of 1 times 2 to the first minus 1 close parenthesis. And this will all be over, here I'll switch the order of the terms, this will all be over 2 to the first minus 1 close parenthesis times pi to the first. And so we want to see if this expression equals 1 over 2 log 2. And the thing to notice here is that concealed within this quotient is a 0 over 0 expression. In the denominator, our first term there, 2 to the first minus 1, that's just 2 to the 0 minus 1, which is 1 minus 1, so that equals 0. And in the numerator, I have cosine 1 pi over 2. Cosine pi over 2 also equals 0. As for all the other terms, they're just constants. I have negative 1 times gamma of 1. Gamma of 1 equals 0 factorial, which equals 1, times 2 to the first minus 1, so 2 minus 1, that's just 1. So the numerator is just negative 1. And then in the denominator, I just have pi to the first. So I have this 0 over 0 expression that we need to evaluate further, multiplying negative 1 over pi. Well, whenever we see a 0 over 0 expression, we know what to do. We use L'Hopital's rule to evaluate it. So let's do that here. So we want to evaluate the limit as n approaches 1 of the expression cosine n pi over 2, close parenthesis, all over 2 to the n minus 1, close parenthesis. Well, this equals the limit as n approaches 1 of cosine n pi over 2, all over 2 to the n times 2 to the negative 1 minus 1, close parenthesis, which equals the limit as n approaches 1 of cosine n pi over 2 over 1/2 times 2 to the n minus 1, close parenthesis, which equals the limit as n approaches 1 of cosine n pi over 2 all over 1/2, and now I'm going to change 2 to the n to e to the log of 2 to the n minus 1, close parenthesis, equals the limit as n approaches 1 of cosine n pi over 2 all over 1/2 e to the n log 2 minus 1. So now we finally have this expression in a form where it's easier to differentiate both the numerator and the denominator. So I'm going to do that here. This is the application now of L'Hopital's rule. I'm going to take the limit as n approaches 1 of, starting with differentiating the numerator, negative sine n pi over 2 times pi over 2. And now differentiating also the denominator, we would have 1/2 times e to the n log 2 times log 2 minus 0, close parenthesis. And now finally taking the limit as n approaches 1, this would give us negative sine of pi over 2 times pi over 2 all over 1/2 times e to the log 2 times log 2. Well, sine pi over 2 is just 1, so this equals negative 1 times pi over 2, or negative pi over 2. And then, of course, e to the log 2 is just 2, so this becomes negative pi over 2 all over 1/2 times 2 times log 2. Those first two terms in the denominator just cancel, and so this simplifies to negative pi over 2 log 2. And so coming back to our original equation, we can replace the 0 over 0 expression with what we found by L'Hopital's rule, negative pi over 2 log 2. And this is still multiplying our constants times negative 1 over pi, so the negative terms cancel, the pi terms cancel, and we're left with this indeed working out perfectly. We have, when we use L'Hopital's rule to evaluate the expression, negative cosine of 1 pi over 2 times gamma of 1 times 2 to the 1 minus 1, close parenthesis, all over pi to the first times open parenthesis 2 to the 1 minus 1, close parenthesis, equals 1 over 2 log 2. Amazing. So it's very cool that that worked out well for a pair of series that we so far were not able to define in terms of the Bernoulli numbers. So now I'd like to ask, again, in the spirit of testing the generality of this functional equation, what if n is a non-integer? Well, to start with perhaps the simplest case, let's let n equal 1/2. Then we would have, substituting the value 1/2 for n into the functional equation above, eta of 1 minus 1/2 over eta of 1/2 equals negative cosine of 1/2 pi divided by 2 times gamma of 1/2 times the quantity 2 to the power of 1/2 minus 1, close parenthesis, all over pi to the 1/2 times the quantity 2 to the 1/2 minus 1, close parenthesis. So then we're going to have eta of 1/2 over eta of 1/2 equals this expression on the right-hand side, and eta of 1/2 over eta of 1/2, of course, just equals 1. So we want to see if 1 equals the expression on the right-hand side of this equation. So the question is, does 1 equal negative cosine of 1/2 pi over 2? Well, that's just negative cosine of pi over 4, times gamma of 1/2, times the quantity 2 to the 1/2, of course, is just square root of 2, minus 1, close parenthesis, all over pi to the 1/2, that's just radical pi, times the quantity, okay, so 2 to the 1/2 minus 1 is 2 to the negative 1/2, which equals 1 over radical 2, minus 1, close parenthesis. But we know from our earlier work on the gamma function that gamma of 1/2 equals radical pi. And if that's at all mysterious to you, please see my previous video on the gamma function where I derived that result. So when we substitute radical pi for gamma of 1/2, we see that the radical pi's cancel from the numerator and the denominator. And then we just need to recall a basic fact from trigonometry, which is that the cosine of pi over 4 equals radical 2 over 2, which is just a fancy way of writing 1 over radical 2. So then we have negative 1 over radical 2 times the quantity radical 2 minus 1, close parenthesis, all over 1 over radical 2 minus 1. This expression then becomes negative 1 times the quantity 1 minus 1 over radical 2, all over 1 over radical 2 minus 1. Then when I distribute the negative in the numerator, this becomes 1 over radical 2 minus 1 over 1 over radical 2 minus 1. And that expression, of course, just equals 1. So this is pretty fantastic. The Eta functional equation appears to also be working for a non-integer input. Well, Euler went on to try other cases and to accumulate more evidence that his Eta functional equation is generally valid. For example, he tested to see what would happen if n were equal to a negative integer and what would happen if n were equal to 3/2. Well, we're not going to do all of that here. Suffice it to say that in every instance, Euler came up with a result that validated his equation. That being said, he didn't really prove it in full generality. This equation, as Euler developed it, is really the work of some very intuitive thinking and conjecture. I mean, it's very deep conjecture, but that's not the same thing as proof. And perhaps that's why, in the decades following Euler's publication of this result, the mathematical community basically forgot about it. And it wasn't until about 100 years later, when Bernard Riemann, using methods from complex analysis and Fourier analysis, proved the Zeta functional equation, which of course is related to the Eta functional equation as we're about to see, that people took notice and went back, and somebody eventually said, hey, Euler actually discovered the Eta functional equation, even though he didn't fully prove it, and there's a good chance that he knew that there was a Zeta functional equation out there as well. Because we're about to see that Euler had at his disposal all of the tools he needed to take the next step to derive the Zeta functional equation. But he never published this. It wasn't until a century later that Riemann discovered it. Now let's first recall the relationship between the Eta function and the Zeta function. We have eta of n equals zeta of n times the quantity 1 minus 2 to the 1 minus n, close parenthesis. Well, to maintain consistency with Bernard Riemann's later work on the zeta function, I'm going to change our variable n to s. So we're going to write eta of s equals zeta of s times the quantity 1 minus 2 to the 1 minus s, close parenthesis. And then for our Eta functional equation, we're going to have eta of 1 minus s over eta of s equals negative cosine of pi s over 2 times gamma of s times the quantity 2 to the s minus 1, close parenthesis, all over pi to the s times the quantity 2 to the s minus 1, close parenthesis. So putting these facts together in the denominator on the left-hand side in place of eta of s, I can write zeta of s times the quantity 1 minus 2 to the 1 minus s. And in the numerator, in place of eta of 1 minus s, I can write zeta of 1 minus s times the quantity 1 minus 2 to the 1 minus s, close parenthesis, close parenthesis. Well, 2 to the 1 minus the quantity 1 minus s is just 2 to the s, so let me write that there. And then I'm going to make one quick simplification. On the right-hand side of this equation, I'm going to multiply that negative 1 into the last term in the numerator, 2 to the s minus 1. So I'll have 1 minus 2 to the s on both sides of this equation, and those terms cancel. So now I would like to isolate zeta of s on one side of the equation. So In order to do that, I'm going to start by just taking the reciprocal of both sides, and so then I'll have zeta of s times the quantity 1 minus 2 to the 1 minus s, close parenthesis, all over zeta of 1 minus s equals pi to the s times the quantity 2 to the s minus 1, close parenthesis, all over the cosine of pi s over 2 times gamma of s. And so again, in an effort to isolate zeta of s, I'm going to multiply both sides of this equation by zeta of 1 minus s all over the quantity 1 minus 2 to the 1 minus s. So we can cancel terms. And so now that we've isolated zeta of s, we have zeta of s equals pi to the s times the quantity 2 to the s minus 1, close parenthesis, times zeta of 1 minus s, all over cosine of pi s over 2 times gamma of s times the quantity 1 minus 2 to the 1 minus s, close parenthesis. And now to simplify further, we're going to multiply the right-hand side by what my favorite high school math teacher called a creative form of 1. We're going to multiply by 2 to the 1 minus s over 2 to the 1 minus s. And when we do that, we get zeta of s equals pi to the s, and now I'm going to do the multiplication, times 2 to the 0 minus 2 to the 1 minus s, close parenthesis, times zeta of 1 minus s, all over cosine pi s over 2 times gamma of s times 1 minus 2 to the 1 minus s times 2 to the 1 minus s, close parenthesis. Well, that 2 to the 0 in the numerator just equals 1, and then we have a 1 minus 2 to the 1 minus s term in both the numerator and the denominator, so those terms cancel. So then we have zeta of s equals pi to the s times zeta of 1 minus s all over cosine of pi s over 2 times gamma of s times 2 to the 1 minus s, close parenthesis. So I'll move that expression to the top line here, and now I just want to do a little bit of work on that gamma of s in the denominator on the right-hand side. Some of you may already know that Euler discovered a beautiful functional equation for the gamma function. This is called the sine reflection formula. It relates the gamma function in an amazing way to the sine function. And the formula states that gamma of s times gamma of 1 minus s equals pi over sine pi s. And I have a video on my channel where I derive this relationship. So if this is new to you, I encourage you to go look at that. And so rearranging, we can write gamma of s equals pi over gamma of 1 minus s times sine pi s. And this is what I mean when I say that Euler could have derived the zeta functional equation. Everything I'm doing here, Euler either already knew or discovered himself. And so now making the substitution that we need for gamma of s, we have zeta of s equals pi to the s times zeta of 1 minus s all over cosine of pi s over 2 times pi over gamma of 1 minus s times sine pi s, close parenthesis, times 2 to the 1 minus s. So that means zeta of s equals pi to the s times zeta of 1 minus s, and now bringing things up into the numerator where they belong, times gamma of 1 minus s times sine of pi s, all over pi times 2 to the 1 minus s times cosine pi s over 2. So I'll bring that equation to the top line here, and then I'm going to make a couple cosmetic changes which will be helpful. I'm going to write in the denominator pi, I'm going to write pi to the first power, and instead of 2 to the 1 minus s, I'm going to write 2 to the 1 times 2 to the negative s. And so then I can cancel pi from the denominator and write pi to the s minus 1 in the numerator. And instead of writing 2 to the negative s in the denominator, I can write 2 to the s in the numerator. So then I have zeta of s equals pi to the s minus 1 times 2 to the s times zeta of 1 minus s times gamma of 1 minus s times sine of pi s, all over 2 times cosine of pi s over 2. But we know from trigonometry that sine pi s is equal to 2 times sine pi s over 2 times cosine pi s over 2. That's just a double angle formula that we all learn in high school trig. So I can write zeta of s equals pi to the s minus 1 times 2 to the s times zeta of 1 minus s times gamma of 1 minus s times 2 times sine pi s over 2 times cosine pi s over 2, all over 2 times cosine pi s over 2. Well, the 2's cancel, and the cosine pi s over 2 terms cancel, and so we're left with our final form of the zeta functional equation. Zeta of s equals, and I'll write zeta of 1 minus s as the last term, zeta of s equals pi to the s minus 1 times 2 to the s times gamma of 1 minus s times sine pi s over 2 times zeta of 1 minus s. Well, I have to put a box around this one. This is just a beautiful formula relating the zeta function on values s to the zeta function on values 1 minus s. And in fact, this is the zeta functional equation that Riemann discovered 100 years after Euler's paper on the eta function. And in some of the sources I've seen, people seem to express surprise that the zeta functional equation should have all these different components to it. Why is there a pi term in there? Why is the gamma function in there? Why is the sine function in there? And I hope that all of you who have taken the time to watch this video can see, because we've gone to the trouble of deriving the eta functional equation as Euler derived it, that these different components of the zeta functional equation, the pi term, the gamma function, the sine function, they all emerge quite naturally from our derivation of the eta functional equation. Well, that's it for today. This has been the longest video that I've made on the channel so far, but I hope that you have all enjoyed it. I appreciate your watching, and if you did enjoy the video, please like or subscribe to my channel. Thanks again.